Today, we're going to look back at a time that, well, it changed everything for all of us. But we're going to do it through a lens you might not expect. We're going to pull back the curtain and look at the invisible blueprint that was guiding the world's response to the crisis. All right, let's get into it.
Yeah, that's a simple sentence, but it carries so much weight, doesn't it? A virus started to spread faster and farther than almost anyone could have imagined. And with it came this huge wave of uncertainty that just washed over everything.
But in the middle of all that chaos, behind every single headline, every public health update, every tough decision that was made, there was this quiet, incredibly powerful force at work. A kind of universal language that helped us predict what was coming, track it, and ultimately fight back. And that force? It was math.
So in this explainer, we're going to break down exactly how math became our guide. We'll look at how it let us decode the virus's incredible speed, what it really meant to flatten the curve, how scientists built models to see the future, and finally, the actual numbers behind immunity.
Okay, so let's start with the big picture. How on earth did math, something most of us remember from a high school textbook, suddenly become a frontline tool in a global health crisis? Well, the thing is, math gave us a playbook when we desperately needed one. This wasn't just theory. It gave epidemiologists and world leaders the tools to try and forecast the spread, to watch infections in real time, and to figure out which interventions, like lockdowns or masks, might actually work. It was even at the heart of planning the vaccine rollouts.
Now, to do any of that, scientists first had to get a handle on the speed and the nature of the virus itself. And this is where two key mathematical ideas, which you probably heard on the news every single day, entered the global conversation. Exponential growth, and this thing called R0.
First up, exponential growth. And honestly, this was one of the hardest but most important things to wrap your head around. See, the virus didn't spread in a nice, neat, straight line. Instead, it was like a car hitting the accelerator hard. The number of cases didn't just add up, they multiplied, doubling and then doubling again.
And this is what that looks like. It starts so small it feels totally manageable, right? One case becomes two become four, no big deal. But the doubling keeps going, and that's the trap. Because very, very quickly, those small numbers just explode into thousands and then millions. That deceptive, explosive power is the essence of exponential growth.
So how do you even measure the speed of that growth? The answer came down to one single powerful number, R0, or R0. This became, you could argue, the most important number of the entire pandemic. It's simple. It just tells us, on average, how many other people one sick person will go on to infect.
And the power of R0 all comes down to one simple threshold, the number 1. Seriously, everything hinged on which side of 1 we were on. If R0 is greater than 1, each sick person infects more than one other person, and you get that out-of-control exponential growth. But if you can push R0 below 1, the outbreak starts to shrink and eventually just fizzles out.
And here's the tough reality we were all facing. Early on, the R0 for COVID-19 was estimated to be somewhere between 2 and 3. Just think about that. That means with no one doing anything, every single infected person was spreading it to 2 or 3 more people. That is a perfect recipe for a runaway epidemic.
Knowing that number, that R0, brought us to the phrase that basically defined 2020, flatten the curve. And this wasn't just a catchy slogan, it was a public health strategy rooted completely in math, with one goal: get that R0 number down.
And the reason for it was incredibly practical and, frankly, terrifyingly urgent. The goal wasn't to just magically stop the virus overnight. It was to slow the spread down so that the number of people who got really, really sick at any one time wouldn't completely overwhelm our hospitals, our doctors, nurses, beds, and ventilators.
This chart shows you exactly what that means. That first bar, that's our hospital capacity. That's the line. The tall bar in the middle, well, that's what an unchecked spread looks like. It just soars right past capacity. That's the nightmare scenario. But the third bar, that shows what happens when we take precautions. The peak of infections is lower, it's broader, and it stays below that critical line.
So if you can track the growth and you understand the goal of flattening the curve, how do you actually predict what's going to happen next? Scientists don't have a crystal ball, but what they do have are mathematical models.
and we're going to look at one of the most classic and important ones. These models are basically really complex simulations. You could think of them as a digital dress rehearsal for a pandemic. They take all the data we have, like R0, how people behave, and they use it to run different scenarios. They help answer all those huge questions like, when's the peak going to hit? And what happens if we close schools versus if we don't?
One of the most foundational models is called the SIR model, and it's actually pretty elegant and intuitive. It just splits the entire population into 3 big groups. First, S for susceptible. That's everybody who could still get sick. Then I for infected, people who are currently sick. And finally, R for recovered or removed, those who survived and are now immune. The model is all about calculating how people move from one of these boxes to the next over time.
And that last box, the recovered box, leads us straight to the final piece of this whole puzzle, the end game. How does a pandemic like this actually end? Well, the answer, once again, lies in the math of immunity.
The concept is called herd immunity. You can think of it like a fire running out of fuel. It's that tipping point where so many people in a community are immune, either from getting the virus and recovering or from getting vaccinated, that the virus just can't find enough new people to infect. It hits a wall and the pandemic fizzles out into much smaller, more manageable outbreaks.
So what is that magic tipping point? Well, it's not a guess, it's a calculation. And the formula is surprisingly simple. It's just 1 minus 1 divided by R0. So if we take that early R0 of 3, you get 1 minus 1/3. And that gives you about 0.67, or roughly 67%. That was the target. About 2/3 of the population needed to be immune to stop the uncontrolled spread.
So when you put it all together, the big takeaway is this. From predicting that first wave to planning the vaccine campaigns, math wasn't just sitting on a shelf. It was an active, essential, life-saving tool. It wasn't just numbers on a page. It was the guide that helped us navigate one of the biggest challenges of our lifetimes.
And that kind of leaves us with one final thought. The pandemic made this invisible math visible to all of us. And it really makes you wonder, doesn't it? What other invisible forces, what other hidden languages of data and science and math are shaping our world right now, just waiting for us to see them?